Before watching this video and the next few, it would be useful to review again videos number 57 and 58, which were on diode models. As discussed in these videos, a useful model is a simplified view of a device using basic circuit elements in order to produce an approximation suitable for doing quick calculations with. In fact, accurate and complex equations for transistors exist. One of the first of these is called the Ebers-Moll model. But the complexity of equations like this mean that although they're suitable for computer simulation and detailed calculation, they are generally too complex for quick back-of-the-envelope calculations. Instead, what we'll do is develop simpler models based on what we know about transistor behavior. The model that I'm going to present here will be suitable for quick but accurate estimates of circuit parameters. So let's start by reviewing what we know about transistor behavior. Firstly, what goes into the collector comes out from the emitter, and this current is set not by the collector emitter voltage but by the base current. So a simple representation of this is shown on the screen. But this doesn't show the base connection. Now we know that IE is equal to IB plus IC, and so we could connect the base to the emitter as shown now. Actually, this isn't accurate either, because it infers that if the base were grounded and the emitter were left unconnected, the collector current would flow out through the base, which of course it wouldn't. But in models, we usually just ignore issues like these, because this isn't and could never be a real circuit. But we do need to remember these limitations. Of course, what does exist is a diode drop between the base and the emitter. Now, if you look back at our earlier videos, you'll see that the diode itself can be modeled a bit like a resistor, which has a value of 25 divided by I, where I is a current in milliamps. And so there we have a basic model. This should make sense to you given what we know about basic transistor behavior. Often, however, it makes sense to redraw this slightly. This is basically done by changing the position of a resistor represented by Re. In the model, we've written it as Re is equal to VBE divided by IE, but we could put it in the base connection. The current going into the base is beta times lower, because IB is equal to IE over beta approximately. So the resistor value is beta times higher. Actually, if you work this out in detail, you'll find it's beta plus 1 times higher. So look at the model now on the screen. This model is sometimes called the hybrid pi model, and we'll look at how it can be used in a couple of videos' time.